Good morning, everyone. It's my pleasure to welcome Stan Owaki, hope I pronounced that correctly, for the colloquium today. So Stan is a professor in the Department of Physics and Astronomy at the University of Delaware. He did his Bachelor of Science in Biophysics at Brown University, and then a PhD in Astrophysics at the University of Colorado in 1982. His postdoctoral work included being a Langley Abbott Fellow at Harvard and also a postdoc at the University of California, San Diego. He has been a faculty member at the University of Delaware since 1987. So his research interests include massive stars and particularly mass loss via radiatively driven stellar winds. Pretty much anything that's close or even above the Eddington limit, whether it's stars, black holes, you name it, and also hot magnetized stars. I think that's more recent with particularly looking at the radio emission, and that's working with Benali Das, who has, have I pronounced that right, but what did I, sorry, what's your name? Sorry, but Bonali, sorry, I apologise for that pronunciation. Bonali Das, who is a postdoc at CSIRO. So thanks also for visiting today. I met Stan during my PhD. When were you in Australia? It was like 2009, and we bumped into each other at Transients Down Under a couple of weeks ago. And it's great that he's visiting Perth and that we can have him for a colloquium. So thank you for coming.
Thanks a lot, Gemma. Yeah, first of all, it's very nice to be here. I've been very impressed with how beautiful Australia is in general, but how modern the facilities are at various universities that I visited in both Melbourne and then here in Perth. And so I'm going to be here until a week from Friday. And I am giving a colloquium at CSIRO next Wednesday on magnetic stars. And I'll talk about that a little bit towards the end of this talk. So what I'm going to talk about today, stand in front of the mic. Okay. Yeah. So basically the idea here is that, well, we're going to talk about Eta Carinae, which should be very familiar to people from Australia because it's in the southern hemisphere. We can't see it from the north, but it's a star that's fascinated me for many, many years. And I was at a KITP workshop in Santa Barbara in 2017 on massive stars, and got into lots of discussions in the residence halls there. I don't know if you know what those are like. It's quite beautiful. You get to sit by this huge fireplace and chat with people. And I got into talking with Phil Podolewski, who does a lot of work on supernovae and mass eruptions and things. And we basically decided that we would get together and try to put together a basic model for Eta Carinae that was based on the idea that it was a merger. And so I'm going to tell you about that work today. It was done with Rio Harai, who was a postdoc at Oxford, where Philip is stationed. I visited there in 2018 and 2019 in the summer. And Fabian Schneider is from Heidelberg. He works on simulating stellar mergers. So I'm framing this talk in this idea that in the modern day, we have this ability to do time domain astronomy. What happened? What's that? A moth? Oh, a moth. As long as it's not a spider, I'll be okay. Anyway, I've been here since mid-January, visiting Monash University in Melbourne. And there was, again, as mentioned, we were at this conference, Transients Down Under. It's all about transient astronomy and time domain astronomy. And the key idea here is that there's all kinds of things now we can discover because we can look at large number of stars in a time domain. And so this is a particular motivation for this talk. There was this, OGLE is this optical gravitational lens event detector that was flown to look for gravitational lensing events, and it happened to serendipitously discover this binary, this contact binary that merged, and it was seen as what's called the Luminous Red Nova. let's say somewhere in between an ordinary classical nova and a supernova. That's why they call it luminous, and it typically is very red. That seems to have triggered this idea that these luminous red novae are often merging stars. So now, in particular, if we look at O and B stars, or massive stars, they are very commonly in binary systems or even triple systems. And it's estimated, this is from a nice review, a paper highly cited, over 1,500 citations, by Husana and Selma Demink and others, about how important binaries are for massive star evolution. And particularly, you see that it predicts that 24%, a quarter of massive stars will at some point merge in their lifetime. So, so what are the time domain signatures of such mergers, massive star mergers? The luminous red novae that Ogle detected was only one solar mass, and most of the luminous red novae events are probably something comparable, a few solar masses. After all, there are many more such stars. But what are the highest mass luminous red novae, and could Eta Car be a prototype for understanding what such a merger, massive star merger, would look like? So here's the Carinae Nebula, taken with HST. This is I think a composite put together by Nathan Smith, and particularly right here is Eta Carinae. And the key thing about Eta Carinae, of course, is that it had this giant eruption in the 1840s, ejected more than 10 times the mass of our sun. This nebula today is expanding at a speed on the order of 600 to 1,000 kilometers a second, depending whether you're at the pole, which is the higher speed, or towards the equator. Sorry for my frog in my throat. You see this equatorial skirt that's probably ejected maybe from the Lagrange points during some kind of merger. That's what we think. But primarily, most of the mass is actually ejected out this beautiful bipolar structure. Even today, however, Eta Carinae is not a supernova. It has some properties that sometimes mask it and make it look like a supernova imposter. But even today, it has a bright star in the middle. Most of the light has been reprocessed by the dust in the homunculus nebula. But when you add up all the lights coming from Eta Carinae today, it's about 5 million times the luminosity of the sun. And the key point about that is that for a 100 solar mass star, the Eddington limit is 3.8 times 10 to the 6 suns. So this, even today, is near or at the Eddington limit, depending on what the actual mass of the remnant star is. And the wind that we see from Eta Carinae today is comparable speeds to the ejecta. So what does this mean? Well, there's this, I'm going to skip this. There's this really nice movie that goes through all the properties of Eta Carinae. If I had more time, I would play it, but I think I'll just skip through it. I was going to use it to show that the nebula today is still expanding. So here, let me just review sort of the key things that as theorists, we're trying to explain about Eta Carinae. First of all, it's huge amount of mass loss that it had over about a few years. It lost more than 10 times the mass of the sun, probably even 20 times the mass of the sun. If that would mean that if it were a stellar wind, it would have to be 1 solar mass per year. Typical hot stars have winds of like 10 to the minus 6 or 10 to the minus 5 solar masses per year for a Wolf-Rayet star, say. So this is really quite remarkable. During its peak, its luminosity was approaching 30 million suns. And the energy in the ejecta is comparable to the luminosity that you observed. So this suggests maybe a coupling between the energy of the ejecta and what is actually powering it. The other thing is that in addition to the stuff that's going in the homunculus, if you look at the outer part of the nebula, there are these fast ejecta, these so-called sprays, that when you date them back dynamically, they go back to like the 12th century. There's various, I'll show you pictures of that. And the third thing is that the current bay Eta Carinae is in a binary system, a highly eccentric binary system. The secondary is actually not detected directly. It's detected through X-rays that happen every 5.5 years when it comes in periastron. And I'll show you some stuff on that. And it's thought that that star, the secondary star, which is probably a quite massive and bright star by itself, but it's not actually seen directly because Eta Carinae is so incredibly bright. So the idea is that this star might be a very powerful wind, but a luminosity less than 1 million suns, say. Okay, so here's the light curve. That's a historical light curve that's been pieced together by records of people who lived in Southern Hemisphere, particularly in Australia, in the past, in the 19th century. And you can see that there's kind of very complex behavior that goes on, extends over many years and even decades. And so this is a very kind of slow evolving event. It's not like a supernova where it just bursts and go off. It kind of has this gradual character to it. One key number here is that, first of all, as I said, the luminosities are over 10 million suns. That's above the Eddington limit. And the dynamical, sorry about this, go back to this. The dynamical age of the current expansion, if you take it back, goes to 1847, which is a little bit after the actual peak luminosity. So that's kind of an important clue. Okay, so the other thing is that, like I said, it's known to be a binary through the X-rays primarily. Every 5.5 years, you get this burst of X-rays, this very characteristic light curve that kind of repeats. It's been now seen 5 or 6 times since it was first detected with various X-ray telescopes. And so I partly got interested. So the idea is that there's binary, that's about the total mass of the binary system from just Kepler's laws is implied to be about 130 solar masses. The eccentricity is about 0.9. And so there's a secondary star that we very mysteriously don't observe, but we know is very important. Now, one of the ways you can try to put a limit on what that star looks like, let's see, there seems to be a delay in this. Okay, so when I first got interested in this by working with a guy named Atsuo Okazaki from Japan, from Sapporo, Japan, Hokkaido, and he was visiting in sabbatical, and we used his SPH code to model the colliding wind binary of the 2 stellar winds that are coming from these 2 stars. And Chris Russell, who's now a postdoc at Delaware, well, research scientist at Delaware, he basically did his thesis on modeling the X-rays. And so I'm going to see if I can get. So this is actually a nice movie he made that as the secondary star plows into the very dense wind of Eta Carinae, you get this nice movie of the X-rays that are emitted from the shocks, from the colliding wind shocks. So applying that quantitatively, he fit the X-ray light curve. In order to do that, he had to assume certain parameters. And basically, that gives you a very strong clue to what the secondary star is. It's very likely a stripped Wolf-Rayet star. Okay, the other thing is this fact that there's an historical, should I go ahead, you go ahead and do that. Okay. There's historical ejecta that is seen at various places in the outer part of the nebula, dating back to an ejecta time, back to the 12th century. And there are various of these. And then finally, so anyway, what would be the source of driving so much mass off the star? Is it a binary merger? Is it some kind of very, very strong wind? And so the answer is, I think it's a combination of those 2 things. And so what we're going to do now is explore review this work that I did with Philip Podgaleski, Rio Harai, and Fabian Schneider, also Nathan Smith, on trying to model this as a binary merger. So this is a very nice graphic that Rio Harai put together. The idea is that this was once a triple system, which was happily had an outer component that was just happily going around. The 2 inner components were just going around. There wasn't much interaction. But then The more massive of the inner binary started to evolve off the main sequence. That caused there to be mass exchange onto the other star. The change in mass, in equalizing of the mass ratio, caused the inner binary to widen. And when it widened, that meant that the outer star now was no longer just a weak perturber. It actually then dynamically started interacting. And so you went through various phases. In this phase 2 here, where there was first mass transfer, then that system became very unstable. It would have lots of close grazings together. And that would eject material in these sprays. And then eventually the system became very chaotic. And the star that lost its mass in the close binary got ejected to be the current day secondary. And then, but in that process, the dynamical instability caused two stars, the two leftover inner stars, to merge. And that led to a huge ejection of mass, but the post-ejection wind from the super Eddington wind basically took that ejecta and swept it up into a shell, which is what we see as to the current day homunculus. So that's the basic scenario. I'm going to walk you through each of the stages of that. So here is just a simulation of two stars that are having grazing incidents with each other. Every once in a while, unfortunately, well, you can just get the idea that every once in a while you get these sprays that eject a lot of material at high speed from the object. And that is basically meant to explain the historical ejecta sprays that we see. The next thing is that the stars, after they have all this mass loss, now become unstable. You get a very unstable triple system. Unfortunately, it doesn't play too well on the screen. Good old Microsoft. But anyway, you get the idea that there's this chaotic swapping of the three stars in randomly. And so we think what ended up happening was the star that was the most massive to start off with transferred its mass on, it was in the inner binary, transferred its mass, then it got ejected into this eccentric orbit. The other two stars are the ones that will then merge. So the next phase is basically the other two stars will then merge, and then the energy associated with the merger is what powers this large mass loss. Okay, so that's where the scenario is. Now, interestingly enough, Fabian Schneider and his group in Heidelberg have been actually modeling with 3D MHD codes the merger of two stars. This particular case is just two 8 solar mass stars. It's intended to model a magnetic star called the Tau SCO, but I'll get to the magnetic field stuff later. And unfortunately, I couldn't find a movie of the merger. It's pretty cool to watch, but we'll save that for another time. And the point is that so this merger then dumps a bunch of energy into the stellar envelope that's already very close to the Eddington limit. So what do you think is going to happen when you have a star that you dump a bunch of energy into kind of impulsively? It's kind of in some ways an externally driven quasi-supernova. I mean, basically you're dumping a bunch of energy, but it's not enough energy to completely explode the star, because after all, the system starts out being bound. But now this merged star has a lot more energy. And so what ends up happening is that energy that deposits into the stellar envelope propagates through the star dynamically as a shock. There's a rebound shock. And then that shock propagates to the surface. And then just like in a supernova, you get a shock breakout. But the material near the surface now has been endowed with a net positive energy. That is, its Bernoulli constant, which is the measure of the total energy per unit mass, is a positive number. The velocity squared times the gravitational minus the gravitational binding energy plus the internal energy from the gas and radiation is now positive. And so that material can basically escape as an eruption. And And so what ends up happening is a certain fraction of the mass from near the surface gets kicked away from the star, follows a similarity solution, just like in supernovae. V goes like R over T. That material that is right near the surface gets kicked at a very high speed, right? But some of the material gets kicked away, but then falls back down. And the dividing line between where that is depends on the details of where you add the energy and how much energy you add. So you're left with an intact star that has ejected a large fraction of its mass, and but it's also still very energetic because some of the mass that it wanted to eject didn't make it and fell back down. So now this star that was already close to the Eddington limit is going to be above the Eddington limit, right? And so it's going to have a really strong stellar wind. So the idea is that now if we look at today, Eta Carinae has a very powerful stellar wind, 10 to the minus 3 solar masses per year. Typical O and B stars, 10 to the minus 6 for O stars, Wolf-Rayet stars, 10 to the minus 5. This is 100 times higher. That's because it's very close to the Eddington limit. It can lose a lot of mass. It doesn't have to use lines. It can just do it with the continuum. And it's basically energy limited, right? When you have, when radiation from electrons drives mass away, it drives as much mass as you can have with your energy. It's kind of what we call photon tiring. And I've done a lot of work on this issue of photon tiring. Anyway, but when we look at this, when we take a slit across the homunculus today, the light that's being scattered by the dust is actually probing the wind from different latitudes. And so when you look at the different latitudes, then you find that over the poles, the wind is stronger and faster than at the equator. You might think that if you spin a star, well, because the star is rotating very fast, you might think that, well, it's going to lose more mass at the equator, but it doesn't have stronger gravity. And so the wind is much faster over the poles. But it turns out for some reason, it also is more powerful over the poles. It also has a stronger mass flux. Why is that? Well, curiously enough, if you just take account of the fact that a rapidly rotating radiative envelope will be gravity darkened by the so-called von Zeipel effect. Radiative diffusion, in some way you can think about it, the star becomes oblate, photons can escape out the poles more easily than they can the equator. And that means you get a more powerful, stronger, faster wind out the poles than you do from a non-rotating star. It's kind of opposite of what you might have intuitively expected. This is something that I discovered with my former student, Steve Kramer, who's now a faculty member at University of Colorado, back in the mid-90s. Okay, so the bottom line is, if you take that into account, then you can kind of do an analytic model of ejecta with wind, post-ejecta wind running into it, that has a latitudinal variation in its mass loss rate and speed. And you can kind of do this analytically. And you get this cool result that depending on how all these different contours are the contours of what you would get if you rotate at faster and faster speed. And you can see it as you rotate close to critical speed, you start making something that looks a lot like the homunculus. So the bottom line is you can make something that looks like the homunculus with more or less a spherically ejected mass from the initial eruption, but then swept into thin shells with the post-eruption wind. Oops. So this is kind of what we end up getting after we put the post-eruption strong bipolar wind into the ejecta. If you didn't have this post-eruption wind, then there would be a lot of ejecta that just barely made it out that would be sitting in the middle of the homunculus. The only way you can get it into this thin shell that we observed is have to have something afterwards sweep it up. Okay, and so that's basically what we think happened in Eta Carinae, that there was an eruption that was induced by the merger, but then the star was super Eddington, very strong, rapidly rotating, and it basically drove this bipolar outflow. So that's the kind of overall scenario that we put forward in this paper. Okay, so this brings us to the question, what are analogs to Eta Carinae today? Well, when I first, when we first started thinking about, when we first did this, we didn't think that it was like just this really beautiful, amazing object that's only 2.3 kiloparsecs away, that 150 years ago or 170 years ago had this giant eruption, and it's just so beautiful. We just wanted to model it and understand what happened to it. But nowadays, with time domain astronomy, this is going to be a pretty rare thing, right? It's not going to be happening all the time. But with time domain astronomy, what do? You look at cajillion number of stars, monitor them with these robotic telescopes, and you basically can find rare things like mergers. And this would be kind of a real jewel if you could find it. And so we want to know whether there are analogs to Eta Carinae among these luminous red novae. And so that's what I've been working on. It's still kind of work in progress. And all I'm going to do here is basically summarize what we think some of the problems, what are the issues are. Well, first of all, this is really kind of different. At the conference in the TDU conference at Swinburne in Melbourne, there was a lot of discussion about supernovae running into pre-supernovae winds. For instance, if the supernova goes off in a red supergiant, the supernova blows into this very slow, very dense wind. Sometimes people think that before the explosion, the supernova explosion, the star has various instabilities and it kicks away material in kind of a mini ejecta. That's kind of explosion into explosion. And of course, you can have stellar winds that evolve from being red giants to white dwarfs, where the slow wind gets impacted by a fast wind afterwards, right? So those are all scenarios that people have explored in the past. But as I kind of made the joke, you think about the upper right, that's kind of like what happens in North America, but we're in Australia, so it's kind of upside down. It's the wind running into an eruption, okay? And that's kind of the key characteristic of what Eta Carinae is. So you have this idea that the shell that forms from the eruption, from the wind that's running into this eruption, that propagates out. And so what we're trying to do is think, well, what are some of the diagnostics? What are some of the characteristics that you would get? For one of the things that you would get is a shock, forward and reverse shock pair. The shocks would then presumably initially be X-rays. So this is just a simple analytic model. All you have to do is solve the conservation of mass and momentum. If you know what the wind speed is, if you know how much mass is made in the ejecta, and I didn't mention this, but there's this cool result that it turns out for this kind of ejecta, there's what's called an exponential similarity relation. It's not like a pure similarity, it has an actual velocity scale associated with it. And so depending on what you choose for the ratio of that velocity scale, the ejecta versus the wind velocity, how much mass the wind is. So this is the plot, for example, as how much energy is emitted by the shock for three different models. V naught over V infinity. V naught is the characteristic of the ejecta. V infinity is the characteristic of the wind. And then over a certain amount of time, how much time does it take the wind to have a comparable amount of mass as the ejecta? Because obviously, if you're going to sweep up the Eta Carinae eruption, you got to have the wind have a comparable amount of mass. It can't just be a puny little wind. It's going to sweep up the ejecta. So anyway, there's lots. I gave a talk on this at TDU. This work in progress. I just wanted to kind of summarize that. And okay, but here's the big wrinkle. So I'm here to work with Bernoulli on these magnetic massive stars. And where do these magnetic massive stars come from? Who ordered them? Because there are stars that have anywhere from 100 to more than 10,000 Gauss that are O and B and A stars. And about 7 or 8% of stars are main sequence stars along that whole sequence, but 8%, 9%. How do they get there? Because they don't have convection zones the way the sun has an active dynamo that makes the sun's magnetic field. So maybe something caused an earlier epoch to have these fields. There's no evidence that the fields themselves are going through any kind of activity cycle. They're pretty much, when we measure them 20 years span, they don't change. unlike the sun, which goes through this activity cycle. So there's a growing idea that maybe these magnetic stars are post-merger objects. And this has been bolstered by a couple of things. One is that this Fabian Schneider's 3D simulation found very powerful magnetic fields get generated in the merger process. And so this could be the origin of this 8 to 10% of stars that are magnetic. They could all be post-merger objects. So this is leads in very nicely to the talk I'm going to give next Wednesday at CSRO on magnetic stars. And if you have time, I hope you'll consider either coming to that or listening to it online. Okay, so this raises the question, a very interesting question. Could Eta Carinae be magnetic? You know? Now, first of all, it would be very hard to detect a magnetic field because the way magnetic fields are detected on these O and B stars is through spectral polarimetry of their absorption lines in their stellar spectrum from the photosphere. This star has a 10 to the minus 3 solar mass wind around it today, and you don't see the actual photosphere of the star. The wind is completely opaque. So all you see is emission lines. And it's very hard, for many technical reasons, it's very, very hard to detect the spectral polarimetric signature, Stokes V polarimetric signature from a star that has emission lines. So you can't really detect them directly, but they could be embedded underneath. Could they maybe help shape the bipolar form? Maybe it isn't gravity darkened, maybe it's just magnetic channeling. Okay, and how strong a field would you need? Well, a lot of the work we've done in massive stars tells you that this would have to be a really pretty powerful magnetic field, more than 20 kilogauss, you know, is the quick estimate to just make it even compete with the momentum of the wind that's being ejected. And but there are magnetic hot stars that have 40 or even 50 kilogauss. And I'll mention this at the talk next Wednesday. And anyway, but it's also predicted by these merger simulations that it should have a magnetic field. So that's kind of a left open question. So I guess I want to conclude here with this idea. Let's just skip back through here. Sorry about this. I want to conclude is Eta Carinae something that is like a Rosetta Stone that's going to tell us about a whole bunch of other objects? You know, like the Rosetta Stone taught us how to translate from one ancient language to another. Is it Eta Carinae a Rosetta Stone, or is it just some weird, crazy thing that, you know, is kind of what we call a red herring? I think you have the same expression in Australia. Red herring is just there to distract you. So, well, first of all, after all, what I've been describing is kind of a pretty crazy process. There's this triple evolution dynamical instability. There's the merger, and there's the post-eruption wind. It all seems kind of contrived and specialized, right? So maybe it's just a very rare kind of beast. Because many people think these mergers that occur in lower mass stars are merging because of the common envelope that forms, and then eventually it just gets dissipated, and the two stars slowly merge. In this case, it's a dynamical merger, just being induced by the dynamical interaction of a three-body thing. But again, massive stars have lots of multiples. And there are a lot of binaries, and they got to have a lot of triples too. So multiples are common in high mass stars. They would have a common envelope system, but with the it wouldn't last that long if it's got a dynamical merger. The common envelope is probably responsible for the equatorial skirt of Eta Carinae. And we see evidence of things called supernova imposters. We see luminous blue variables. Eta Carinae is the king of them all, but there's evidence from people who look at light curves. And after all, gravitational waves form from black hole merges of what was once main sequence massive stars. So if gravitational waves can do it, why can't massive stars do it, right? So, and then the whole point is that with time domain astronomy, you're looking at enough stars, you know, with LSST, Vera Rubin telescope that's now going to be commissioned in the next couple of years. This could be, it could, you know, we could be finding analogs to Eta Carinae. So I think the answer to whether is Eta Carinae a red herring or Rosetta Stone is probably something like it's a Rosetta herring. That's my joke. You have to have one joke in a thought. Everybody goes to sleep. Okay, so this is my summary. Energy from the merger of massive stars induces the prompt ejection of mass. That gets swept up. I didn't talk about the exponential similarity relation, but there it is. Post-eruption has a super Eddington wind, which can blow the eruption, the ejecta, into a shell, bipolar shell. And this could have signatures in X-rays, broad emission lines, and so forth. Dust will eventually form. So basically, even though Eta Carinae has a very complex light curve, you can kind of look for something that looks like that and look for other signatures. Of course, we can't go back in time and look at Eta Carinae and see if it had X-rays during the giant eruption. But there is this interesting thing that I didn't get a chance to mention, that because Eta Carinae is surrounded by such a complex amount of interstellar material, you can see light echoes from the great eruption, and then you can find out a lot more. You don't have to just rely on historical data. Okay, so so the question is whether it's a prototype for merging massive stars in external galaxies, like luminous red novae, the most luminous red novae. Okay, so that's my talk. But before I go, it's like, you know, whenever you present something, you have to watch an ad. So the ad here today is that I love to teach, and over the years, I've been teaching a course called Fundamentals of Astrophysics. I've been teaching it for about over 15 years. I'm retiring this summer, so that's why I'm able to come here. And this is only $35 US dollars on Amazon for a textbook. That's pretty cheap. And it covers everything from stellar properties all the way to the Big Bang. And I use it for a course in one semester. I teach students who are calculus-based physics, have had either science or engineering majors. And if you have people here that are teaching similar courses, you might want to take a look at that book and see if you might. Thanks very much for your attention, and I'll take any questions you might have.
Sure, that was absolutely fascinating talk. Very spectacular. We'll start with the person from the room. I don't know.
Okay.
I think so. Yeah, fantastic talk, really interesting. Two questions. One is, you talked a lot about mass loss, but it looks like especially for high redshift galaxies, we need harder for photoionization from these massive stars. And do these like high energy photons, do they come during the merger phase, or are they generated throughout the lifetime of these massive binary systems?
Well, I would say Eta Carinae, actually, when you look at its spectrum from light echoes, it's actually very cool. It's more like 7,000 or 8,000 Kelvin effective temperature. That's because it's such an incredibly optically thick envelope to wind. So any light that's coming from, even though it's very luminous, it comes out at a huge radius. So Eta Carinae itself would not be the best. That kind of merger would not be the best. But O and B stars, Wolf A stars and O stars, they're just pumping out UVs like crazy. You know, they make H2 regions and all that stuff. And so I would say it's more when they're not merging that they provide your ionization. But of course, you know, the whole point being that when you look at a picture of a galaxy, where do you see ultraviolet coming from? It's all these places where hot stars are being formed, all the H2 regions. You know, take a look at the Whirlpool galaxy, and there's all these little red splotches. That's all H alpha coming from H2 regions. So if you want a source of UV light, massive stars, which are of course they only live a short amount of time, so you see them in star forming regions. That's where you get them. Yep. And, but of course, you know, the way in galaxies, or at least active galaxies, you get lots of that from the central AGN and stuff like that. And it's a big debate about which one is more important for reionizing the universe, right? But I don't think these are the relevant. This is more relevant for the transient stuff.
Okay. Thank you. Sorry.
Go ahead.
I have another question.
Fine, it's great.
You mentioned that 7 to 8% of the OB and A stars, they have gone through the merger.
Well, they're detected to be magnetic.
Yeah.
This is one of the great things. There's this famous joke that magnetic fields are to an astrophysicist what sex is to a psychoanalyst, right? That's a joke. I don't know if I can use it anymore. Maybe I can't anymore. But anyway, and the point is that the reason I say that is that normally we're living in the dark. It's like, oh, let's invoke magnetic fields when we can't explain something. But in these stars, we actually detect these magnetic fields through spectral polarimetry. We know the magnetic field strength. And moreover, we know exactly how their winds are driven. They're driven by line scattering off of photons from the star. This is a very well-established theory going back to Kastorov and Klein. So you put that together and you can make all kinds of really nice models of that. And you find that there's about 8 or 10% of O, B, and A stars all the way. An O star might have 60 solar masses, an early O. An A star's got 2 solar masses. Through that whole range, there's 8% that are magnetic. So how does that happen through mergers, for example? How is it? And why is it just this constant 8%? That's still a mystery. And if it is mergers, some people think it's mergers, some people are still skeptical about that. I'm in the middle.
Sorry, my question was, if they have magnetic, if they are formed by merger, you said that during a merger, the stars undergo through a significant mass loss, right? So how can you form, is it still possible to form such a large fraction of O and B star? I guess you may have said that.
Well, this goes a little bit into the area of what I'm going to talk about on Wednesday, but you have to ask yourself, who's the boss? If you have a magnetic field, okay, and you have a wind, who's the one that's more powerful? And so that's characterized by a parameter we call the magnetic confinement parameter. And then you can ask yourself, for a given mass loss rate, how powerful does the field have to be to dominate the wind, at least near the star? And it turns out that, the fields that we see, these are very powerful winds, but the fields that we see from these stars are kilogauss, and it basically traps the wind and makes the magnetosphere. The question is what do you have a wind? If you have a wind that's as powerful as 1 solar mass or 1 solar mass per year, you'd have to have a magnetic field that's like almost getting up towards 10 to the 5 Gauss, 100 kilogauss. Is that really happening? But if you look at that slide from the merger simulation, they were really huge fields in there. So, but then what happens, if that happens, the wind doesn't want to escape out the equator because it's closed if it's a dipole. It wants to go out the poles. So maybe this is playing a role in the bipolar nature of Eta Car. Thank you for your questions, really good ones.
I also have a couple of questions, but
I'm sorry?
I also have a couple of questions. So my first question is about Tausco, that it has a somewhat more complex field compared to the other stars. So I'm just curious, is it possible to create an ordered dipole-like field from mergers?
Well, that's a good question.
From simulation.
That's a good question for people who are more expert than I. But here's my intuitive answer. When you form such a field, it forms from very complex convection cells. Look at the field of the sun. It's very complex. But when it declines to minimum, you can kind of globally model it as a tilted dipole, right? Now, the sun is actively being generated by a dynamo. But now if you're going to do this in an event, the first thing you're going to do is probably create some very complex fields. But the higher the order of the field, the more dissipative it should be. It should decay quicker. So Tausco has a complex field which suggests it's actually had this merger occur relatively recently. But most of the other O and B stars are pretty well approximated by tilted dipoles. And it suggests that they've had their field a little bit longer and the ohmic dissipation has settled on the longest. The largest mode means the longest decay time. So I think that it has to do with age of post-merger.
Can I
That
ask
good?
one more? Or maybe?
Sure.
So my other question is, because you didn't mention anything about radio, so I'm just curious, is there any radio signatures of during periostrone, because it's a binary system?
That's a good question that I do recall hearing that that Eta Carinae is observed and detected in the radio as well, by the way, in gamma rays. Gamma rays are probably generated from the shocks, acceleration, particle acceleration and shocks, but it's actually a very good question that I should have, in giving this talk and knowing who the audience is, I should have had that. But I do recall people observing Eta Car. Anybody here know what are the observational characteristics of Eta Car in the radio? I just, being a theorist, I can only keep so many facts in my head, you know. Thanks. Hi, Kevin.
Yeah, really great talk. What is the lifetime of the nebula? Because if you've got 8% potentially of these massive stars are, or ABOs are actually magnetic, how long would these nebula stick around for?
Well, I think the question of whether they're magnetic or not is much more speculative than everything else I've told you. I actually think the case is pretty clear that Eta Car was a merger. Okay, triple evolution dynamical instability induced merger. That basically it had to do with the fact that because we see it's a binary today, if it's a merger, it had to be a triple. Triples are unstable. So I actually think that the case for all the things that it fits. Now, it doesn't fit everything. There are still things like the little homunculus and little burps and things. It's like any theoretical model, it has to, it struggles to explain more than one thing at once. And this explains, 3 or 4 things. So I think it's a pretty strong case that it's a merger. Whether it has embedded in it a magnetic field is another issue. But what we're finding is that there are clear evidences of stars that have gone through some crazy evolution. There's this new star called the quasi-Wolf-Rayet star that was discussed by Tomar Schrenar in a science paper last year. I think Bernalini gave a journal talk on it recently. Anyway, I think there's a lot of building evidence that the magnetic fields we see from O and B stars could be from mergers. That's another separate topic. But then asking yourself, how long will they last? How long will this type of event last? I think you can see it in Eta Carinae. It's been 200 years, and we're still seeing something that is 5 million suns. and in other words, the dynamics is very prompt, relatively prompt. It occurs over a few years. But then there's this thermal time scale where this star has now got all this extra energy, and it has to get rid of it on a thermal time scale, which could be should be centuries, even 1,000 years. And now the nebula will get more dissipated over time. So a good question would be, what would Eta Carinae look like 1,000 years from now? Yeah, and but I would speculate that it would still be a quite luminous star, and that it would have a beautiful nebula around. If it was something that you could actually detect the nebula or signatures of the nebula, I think it would still be sticking around. And then I didn't get a chance to talk about all the outer stuff of the outside the homunculus. There's a whole bunch of stuff that you see in X-rays, for example. So that's clearly, like, what I'm trying to say is that the ejecta, when it went off, some of that stuff went off at 5,000 kilometers a second. It's like a supernova explosion. It has some stuff, and that stuff runs into whatever is the interstellar medium. So there's lots of evidence of being surrounded by a cloud of X-rays. So all those things are really good questions. But I guess I'm trying to say is that this kind of thing lasts much longer than a supernova or other kinds of transient events.
I guess what I was sort of thinking is if all of these other stars, potentially this 8%, actually result from mergers, then would we see more of these nebula?
Yeah.
Or are the nebula short-lived enough that we don't?
That's a good question. So I think people have done that. In some cases, there is stuff that's surrounding them, particularly for the ones that are thought to be. I think in Tau Skov's case, I think there's some evidence that there's stuff surrounding it. But again, if these magnetic fields last for 100,000 years, that's a long time for a nebula to stick around. Okay, so, but people are doing that experiment. They're basically taking a look at these O and B magnetic stars and seeing what's around them. And then I should also mention that when this happens in an O star, you have a strong magnetic field and you have a powerful wind. What's that going to do? It's going to spin the star down. It's going to lose angular momentum. And so we have one O star that's magnetic that's got a inferred rotation period of 50 years. Okay. And, but there are B stars that are rotating so fast that they have, this is what I'll talk about on Wednesday. They basically have that the co-rotation of the field and forces gas to be rigidly body rotating, and then that material wants to fly away, but it's being held down by the magnetic field. We call these centrifugal magnetospheres. And there's evidence, there's a lot of work that Bernally and I are working on those stars. Anybody else?
Are there any questions from online attendees? If you do, please feel free to unmute and ask your question. Okay, so while waiting for another question, I have one, but beyond the side point that you made. So among the different observational probes, you also mentioned prospects of detecting gravitational waves from this type of mergers. So,
well, from the stars that don't merge on the main sequence, these are merging non-evolved stars.
Right.
But if they don't merge until they go supernova, and then they're left behind very massive black holes, and then they can merge just by giving off their gravitational wave energy, and then they merge. That's what happened to the famous 2015.
Okay, so those type of, so I thought that maybe like there is some sort of a signal expected from the initial merger.
Yeah, these are too big and fluffy to make much gravitation.
Sure. Okay.
You have to have very compact objects, either a black hole or a neutron star. There's some possibility we'll be able to detect white dwarfs merging with gravitational waves, but you can't really detect the gravitational waves because the gravity, the gravity in these stars is like the sun, or it's not like black hole where the escape speed goes to infinity.
Yeah. So what I was curious was, is that because you mentioned like 24% of them are like this merger class, and the lifetime of the nebula is like maybe 100,000 million years kind of a thing. So is this a significant enough population that something like, advanced LIGO or other detectors?
Well, one of the key questions is, what happens to these magnetic stars when they finally do explode as supernovae, right? And one answer is they make magnetars. That's what people think. That's what people think happens in this quasi-Wolf-Rayet star that I told you about. You take the magnetic field of these stars and you compress them down to the size of a neutron star. You've got 10 to the 15 Gauss. So they could be the origins of magnetars. At least some of them could be. It could be one source. Maybe there's more than one.
Right. So that process could generate like a gravitational waves, and that.
Well, then this is an issue that people at the TDU conference were discussing: is what are the gravitational waves of core collapse? What are the gravitational wave signatures of core collapse? And it's much harder to detect. But with these new one of the things I learned, Yeah, no, I'm saying that with these new gravitational wave anticipated things, this Einstein telescope and this CE telescope, well, LISA is going to be in space. That'll probably detect things like supermassive black holes merging, but the ones there's this CE. What does that stand for? We learned about it at the TDU. There are two different telescopes being developed. This Einstein telescope, which will have much higher sensitivity than, I guess because they have, well, there's lots of things they can do to improve it. They showed this graph of like the signal to noise that goes down as they make these bigger and bigger telescopes for gravitational waves. one of the things that I love to teach about in my class is that when you improve the signal to noise in a gravitational wave detector, you can detect twice, sensitivity by a factor of 2. Gravitational waves only decay in their amplitude by 1 over distance, unlike the flux. So that means you have 8 times more sources every time you improve a factor of 2. So we're already at the point where we're detecting gravitational waves every few days. When we do this with these big telescopes, this Einstein telescope, it'll be dozens a day. And you'll be able to detect much fainter things like white dwarfs merging, neutron stars merging, and potentially supernova too. Yeah, so that's exciting. And I'm not a gravitational wave astronomer. I have a nice anecdote to tell. I was invited to be on the so-called decadal survey in the United States. Every 10 years, they do a survey of what's the big thing in the next 10 years. Where should we put our resources? The National Academy does this. And I was honored to be able to be on a committee on stars. And this was in 2010, and everybody was talking about they're going to detect gravitational waves in the next decade. And I said, so what? You can see a little blip, And I mean, when you think about stars in astronomy and all the spectra you get, and all the information you get, and this is not going to be able to see it in light. All you're going to see is this little blip in the gravity. Well, of course, what we've learned about since then is that that little blip contains enormous amount of information that you can't get any other way. And then if you're a neutron star merger, then there's an electromagnetic counterpart. And so now we're off to the races, right? So if we could detect more of these neutron stars, which are these short gamma ray bursts, and that future astronomy is, but it's kind of vexing. That was 2017 that they detected those neutron star pair that happened to be very close. We were very lucky. And it's been now 7 years, and it's only 1 or 2 other candidates, as I understand, of the. Yeah. Anyway, but eventually they got to start showing up, and as they build these more and more sensitive things. So gravitational wave astronomy is, if I were a young astrophysicist, that would be an area I'm rather interested in. Okay.
Any more questions from the room? I don't see anything from online. Last call for questions. Any online attendees, if you want to ask, please stand or unmute. If not, we are well past the hour. Just
okay.
So let's thank once again Stan for fantastic information, and also
put up my ad. Yeah. Thanks a lot. I really enjoyed it, and I look forward to. I'll be here until a week from Friday.
Yeah.
A week from.
It might take 15 minutes because I just. So I will send an email, but don't exceed it. Yeah. I did place an order before coming. Yeah.
Okay, so you get some pizza now?
I hope so, but 15 minutes.
Okay, that's fine. We just,
Yeah.
I always have to come down. Give a talk. They're always a bit. I don't know when you go teaching. Something. I read a class.
Yeah.
With your phone.
If you wanted to go back, that's what you want to do. Would you go and sit outside? Yeah.
We can chat a little bit about the